In 1952, a fossil hunter named George Sternberg pulled something extraordinary out of the chalk beds of western Kansas. It was a fish, 13 feet long, with jaws built for killing and a body designed for speed. But the remarkable thing about this fossil was not the fish itself. It was what was inside it. Perfectly preserved within the ribcage, almost entirely intact, was a second fish, 6 feet long, swallowed whole. The larger fish, Xiphactinus audax, had eaten the smaller one, Gylicus arcuatus, head first, and then died almost immediately, likely because the prey, still alive, ruptured a major organ during the struggle. The predator and its last meal sank to the seafloor together and were buried in the sediment, locked in the same position for 80 million years. That fossil, known as the fish within a fish, now sits in the Sternberg Museum of Natural History in Hays, Kansas, mounted behind glass in the same configuration in which it was found, the smaller fish still perfectly visible inside the ribcage of the larger one. It is one of the most famous and most photographed fossils in all of paleontology, and visitors who see it for the first time invariably ask the same question. What kind of ocean produces a predator so reckless that it dies from eating something nearly half its own length? The answer is an ocean where competition for food is so intense, and the risk of losing a meal to something bigger and faster is so constant, that gambling your life on an oversized kill is a more viable strategy than letting it swim away. Xiphactinus did not die from bad luck. It died from a survival strategy that made sense in a body of water where hesitation meant starvation and every meal might be your last. That is the kind of ocean the Western Interior Seaway was. But the reason this fossil matters for the story we are about to tell is not the drama of the kill itself. It is what it tells you about the ecosystem both of these animals inhabited. Because Xiphactinus, as large and ferocious as it was not the apex predator in this ocean. It was not even close. It occupied the middle of a predator hierarchy that included animals 3 times its size, armed with weapons that made its fangs look modest, hunting in the same water at the same time. Xiphactinus was a mid-tier killer in a marine ecosystem so densely packed with predators at every depth and in every ecological niche that the Western Interior Seaway of the late Cretaceous may have been the single most dangerous body of water in the entire 4.5 billion year history of the planet. This was not an ocean in the way you normally think of one. It was an inland sea, a vast, warm, shallow corridor of saltwater that split the North American continent in two from the Gulf of Mexico to the Arctic Ocean. At its maximum extent, roughly 80 to 90 million years ago, it stretched over 1,000 miles from east to west and covered what is now the Great Plains, the Rocky Mountain foothills, and everything in between. Kansas, Nebraska, the Dakotas, Montana, Colorado, Texas, the entire midsection of the continent was underwater. Denver was on the seafloor. Dallas was near the shoreline. The sea reached depths of up to 400 meters in some areas, with most of it considerably shallower, and the water temperatures were tropical to subtropical, comparable to the modern Gulf of Mexico or the Caribbean. Warm water, abundant sunlight penetrating through the shallow depths, and nutrient upwelling from the deeper channels created conditions of extraordinary biological productivity. The water was not clear, tropical blue. It was green with life. Phytoplankton bloomed in the sunlit upper layers, feeding vast populations of small fish and invertebrates. Ammonites, those ancient coiled shell cephalopods, drifted through the water column in enormous numbers, some of them exceeding a meter in diameter. Giant clams filtered the bottom. Sea turtles the size of automobiles, including Archelon, which reached 15 feet in length and weighed over 2 tons, cruised the shallows. Hesperornis, a toothed flightless diving bird that looked like a penguin crossed with a dinosaur, hunted fish from the surface, propelling itself underwater with powerful hind limbs and seizing prey with jaws still lined with teeth that its modern bird descendants have long since lost. Life thrived in this seaway, and because life thrived, predators thrived. They thrived in a concentration and diversity that has no equivalent in any modern ocean. What made the Western Interior Seaway uniquely dangerous was not any single predator. It was the layering. Every depth zone from the surface to the seafloor was occupied by a different class of killer, each adapted to hunt in its own specific realm, but capable of striking into adjacent zones when opportunity presented itself. There was no safe depth. There was no refuge. If you were a fish, a turtle, a marine reptile, or anything else swimming in this water, something above you, below you, or beside you was hunting you at all times, and the predators themselves were hunting each other. Start at the surface. Above the waterline, Pteranodon soared on a wingspan of up to 7.5 meters, roughly 24 feet, scanning the water below for fish near the surface. It was one of the largest flying animals of the late Cretaceous, and the Seaway was its primary hunting ground. But Pteranodon was not safe either. Fossil evidence shows that the giant shark Cretoxyrhina attacked Pteranodon from below. A specimen described in a peer-reviewed study contained a Cretoxyrhina tooth wedged beneath the vertebra of a Pteranodon, direct physical evidence of the shark biting the flying reptile, likely when it dipped to the surface to fish. Whether the bite was predation or scavenging is debated, but the implication is clear. Even the animals hunting from above the water were not beyond the reach of what lived beneath it. Just below the surface, in the open water column, the Mosasaurs ruled. And ruled is not an exaggeration. Mosasaurs were marine lizards, descendants of small terrestrial monitor lizard ancestors that had returned to the sea sometime in the early late Cretaceous and, over roughly 30 million years of evolution, transformed into fully aquatic predators that bore almost no resemblance to the land animals they had once been. Their legs had become paddle-shaped flippers. Their tails had flattened into powerful, laterally compressed swimming organs that propelled them through the water with sinusoidal undulation, similar to the movement of a modern sea snake but at vastly greater scale. Their skulls had loosened at the jaw joints, developing a degree of cranial kinesis that allowed them to flex their jaws outward and swallow prey larger than their heads, a trick inherited from their snake relatives. By the late Cretaceous, Mosasaurs had diversified into over 70 documented species worldwide, filling ecological roles from small, agile fish hunters to enormous apex predators that rivaled anything alive in the ocean today. And in the Western Interior Seaway, they were the unchallenged dominant predator group. The largest of them, Tylosaurus pruriger, reached lengths of 40 to 45 feet. Picture a Komodo dragon stretched to the length of a school bus, with flippers instead of legs, a massive tail for propulsion, and a skull over a meter long, armed with rows of conical teeth. Its palate carried a second set of pterygoid teeth that functioned as a biological conveyor belt, gripping prey and forcing it down the throat, preventing escape once the initial bite landed. This is a trait shared with modern snakes, and it made Tylosaurus an exceptionally efficient killer. Once those jaws closed, the prey was going one direction only. Tylosaurus ate everything. Gut contents and associated fossils show it consumed fish, sharks, smaller mosasaurs, plesiosaurs, diving birds, sea turtles, and ammonites. It was not a specialist, it was the ultimate opportunistic apex predator, killing whatever it could catch. And at 45 feet long, with a bite powerful enough to crush the armor of a sea turtle, it could catch almost anything in the Seaway. But Tylosaurus was not alone. The Mosasaur guild in the Western Interior Seaway included multiple coexisting species, each adapted to a slightly different ecological role. Clydastes, a smaller and more agile mosasaur reaching about 12 to 15 feet, was likely a fast-pursued predator that targeted fish and smaller cephalopods. Platecarpus, slightly larger, was one of the most common mosasaurs in the Seaway and appears to have been a generalist, feeding on fish and soft-bodied prey. A 2026 study from the University of Liège used three-dimensional biomechanical simulations of 16 different Cretaceous marine reptile jaws to show that mosasaurs and plesiosaurs had fundamentally different biting capabilities, allowing them to coexist by hunting different types of prey with different methods. Mosasaurs, the study found, were built for powerful, crushing bites. Plesiosaurs were built for fast, snapping strikes. Same ocean, same prey base, different tools, different targets. The Seaway was not a single predator's domain. It was a cooperative nightmare in which every hunting strategy was represented simultaneously, and a 2025 study added another layer of complexity. Isotope analysis of mosasaur teeth from Hell Creek Formation deposits in North Dakota showed that some mosasaurs were not confined to the open ocean at all. They were entering freshwater river systems, following prey upstream into environments that had previously been considered beyond their range. The Western Interior Seaway's predators were not contained by the seaway's boundaries. They were pushing into the rivers that fed it. Deeper in the water column, the Plesiosaurs occupied a different predatory niche entirely. Elasmosaurus platyurus, one of the most iconic marine reptiles of the Cretaceous, and one of the most anatomically bizarre predators in the history of vertebrate evolution, reached lengths of over 40 feet, but more than half of that length was neck. Its neck contained over 70 vertebrae, making it proportionally the longest neck of any animal known relative to body size. The neck was not muscular and flexible like a snake. It was relatively stiff, with limited range of motion at each individual joint, but the sheer number of joints gave the complete structure a sweeping, curved flexibility that could reach in a wide arc around the animal's body. Current research suggests Elasmosaurus likely used its extraordinary neck to reach into dense schools of fish from below or from the side, snatching individual prey items with rapid lateral strikes of its small, tooth-studded head while keeping its massive, four-flippered body at a safe distance. The body stayed hidden, or at least far enough away to avoid triggering the flight response of a fish school, while the head moved independently through the kill zone on the end of that impossibly long neck. Think of it as the Cretaceous equivalent of a fishing rod attached to a submarine. Elasmosaurus was not alone in its niche. Polycotylid plesiosaurs, by contrast, had much shorter necks and proportionally larger heads, built for faster, more aggressive pursuit hunting. The 2026 biomechanical study from the University of Liège modeled the jaw mechanics of both groups and found that while mosasaurs were built for powerful, crushing bites capable of processing hard-shelled prey and large, struggling animals, plesiosaurs, particularly the long-necked elasmosaurs, were built for rapid, snapping strikes suited to catching small, fast-moving fish and squid. The two groups were not competing for the same meals. They were hunting different targets with different strategies, coexisting in the same water column by partitioning the prey base between them. This ecological separation is why the Western Interior Seaway could support such an extraordinary concentration of large predators simultaneously. They were not all chasing the same food. They were dividing the menu. Neither group was safe from the other, or from anything else in the seaway. Fossil evidence shows mosasaurs preying on plesiosaurs, with Tylosaurus specimens found in association with partially consumed elasmosaur remains. At least one plesiosaur specimen shows bite damage consistent with a mosasaur attack that the animal survived, with healed bone indicating the plesiosaur escaped but was badly wounded. And the violence was not limited to interspecific competition. Mosasaur fossils with bite marks from other mosasaurs of the same species are well documented, indicating that these animals fought each other over territory, mates, or food, inflicting serious injuries and sometimes killing each other in the process. The Western Interior Seaway was an ecosystem where the predators did not just hunt prey. They hunted each other, they fought their own kind, and they existed in a state of constant, overlapping, multi-directional threat that is difficult to overstate. In a modern ocean, an apex predator, like a great white shark, has relatively few enemies. In the Western Interior Seaway, every apex predator had at least one enemy that was bigger, faster, or better armed, and the apex of the food web was not a single species sitting comfortably at the top. It was a contested, violent, perpetually shifting competition among multiple lineages of giant marine predators, each capable of killing the others under the right circumstances. And below and between all of these large predators, the Seaway supported a vast guild of smaller hunters and scavengers that filled every remaining niche. Enchodus, the saber-toothed herring, was a small but aggressive predatory fish with oversized fangs that hunted in the mid-water column. Giant squid ancestors pursued fish and ammonites in the deeper channels. Ammonites themselves, though primarily prey, were active predators of smaller invertebrates and planktonic organisms. The seafloor was carpeted with filter-feeding bivalves and brachiopods, scavenging crabs and gastropods, and the occasional bottom-dwelling shark like Squalicorax patrolling for carcasses. Every level of the food web was populated. every calorie that entered the system was fought over, consumed, and recycled with an efficiency that left nothing to waste. Then there was the shark, Cretoxyrhina mantelli, nicknamed the Ginsu Shark for teeth so sharp they could slice cleanly through bone and leave cuts as smooth as a surgical incision, was the great white of the Cretaceous. It reached lengths of 7 to 8 meters, roughly 22 to 25 feet, and it was built along the same lines as the modern lamnid sharks. Streamlined, powerful, fast, with a conical snout, large eyes adapted for hunting in variable light conditions, and a mouth that could open wide enough to take enormous bites. Its teeth were distinctive, up to 7 centimeters long, curved, smooth-edged rather than serrated, with a thick enamel coating that gave them extraordinary durability. The jaws contained up to 7 rows of teeth, with 34 teeth in each row of the upper jaw and 36 in the lower. Where mosasaur teeth crushed and mosasaur jaws clamped, Cretoxyrhina teeth cut. Clean, deep, slicing wounds that removed large sections of tissue in a single pass. The nickname Ginsu was not a joke. It was an accurate description of the feeding mechanism. And the fossil evidence of predatory behavior is unusually direct. This is not an animal whose diet is inferred from tooth shape or ecological modeling. Its teeth have been found physically embedded in the bones of its prey. Cretoxyrhina tooth fragments have been recovered lodged in the vertebrae, ribs, and limb bones of Mosasaurs, Plesiosaurs, Xiphactinus, and even Pteranodon. In each case, the tooth was driven deep enough into the bone that it snapped off and remained in place as the prey escaped or the carcass sank to the sea floor. These embedded teeth are direct physical evidence of predatory attacks, as close to a photograph of a Cretaceous hunt as the fossil record can provide. Cretoxyrhina did not just eat fish. It attacked the seaway's other apex and near-apex predators. It is one of the few animals in the fossil record for which we have direct physical proof that it routinely hunted other large predators. The Niobrara chalk of Kansas has also produced several remarkable Cretoxyrhina specimens preserved as shark mummies, with not just teeth, but complete jaw structures, vertebral columns, dermal scales, and even stomach contents preserved in 3-dimensional detail. These specimens show that Cretoxyrhina's body was almost identical in overall layout to a modern great white, reinforcing the ecological parallel. It occupied the same niche in the Western Interior Seaway that the great white occupies in the modern ocean, but in an ecosystem that was warmer, shallower, more productive, and stacked with prey that no modern shark will ever encounter. But Cretoxyrhina also had its own predator, Tylosaurus. Remains of Cretoxyrhina have been found within Tylosaurus gut associations, indicating that even the great white equivalent of the Cretaceous was not safe from the mosasaur sitting at the very top of the food web. In the Western Interior Seaway, nothing was exempt from being hunted. Every predator was simultaneously someone else's prey. The food web was not a pyramid. It was a web in the truest sense, with lines of predation running in every direction, including back toward the top. And then, in the middle of all of this, swimming through the same water as 45-foot mosasaurs and 25-foot sharks and 40-foot long-necked plesiosaurs, was Xiphactinus. The fish that started this story, Xiphactinus audax, was one of the largest bony fish in the Cretaceous ocean, reaching lengths of 15 to 20 feet with a bulldog-like face, a protruding lower jaw lined with large interlocking fangs, and a powerful, muscular body built for explosive acceleration. It was not a graceful cruiser. It was a ram-feeding ambush predator that launched at prey from close range, opened its enormous mouth, and swallowed the target more or less whole. Its common nickname, the bulldog fish, captures the animal's essential character: aggressive, fast, and not particularly concerned with whether the prey was a manageable size. At least a dozen Xiphactinus specimens have been recovered with the remains of large, undigested prey still visible inside their rib cages, indicating that Xiphactinus routinely attacked and swallowed fish that were dangerously close to its own body size. This was apparently not a rare behavior or a desperate act. It was standard operating procedure. The fish within a fish. Fossil is the most famous of these specimens, but the pattern it represents, a predator dying from its own kill, appears repeatedly in the Xiphactinus fossil record. The prey, still alive inside the stomach, would rupture a blood vessel or organ during its final struggles, killing the predator from the inside. Xiphactinus apparently made a career of eating things that were almost too large to eat, and the fossil record suggests this strategy killed individual animals regularly. One specimen was even recovered with a mosasaur flipper clamped between its jaws, evidence that Xiphactinus either attacked a juvenile mosasaur or scavenged a carcass, and died in the attempt. Ambition, in the Western Interior Seaway, was frequently lethal. Xiphactinus was hunted by Cretoxyrhina. A nearly complete Xiphactinus skeleton was found preserved inside a large Cretoxyrhina specimen collected by the pioneering fossil hunter Charles H. Sternberg, now on display at the University of Kansas Museum of Natural History. The predator of the Seaway's fish was itself the prey of the Seaway shark, and that shark was itself the prey of the Seaway's mosasaur. Tylosaurus gut associations include Cretoxyrhina remains. The chain of predation ran 3, 4, 5 links deep before it reached an animal that nothing else in the ecosystem could reliably kill, and even Tylosaurus was not truly safe. Tylosaurus specimens have been found with bite marks from other Tylosaurus individuals, indicating intraspecific combat or cannibalism among the apex predator itself. In the Western Interior Seaway, even the top of the food chain was not a peaceful place. This interconnected web of predation extended to the scavengers as well. Squalocorax, sometimes called the crow shark, was a smaller, widespread shark that appears to have functioned primarily as a scavenger and opportunistic predator. Its teeth have been found associated with the carcasses of mosasaurs, plesiosaurs, hesperornis, and even hadrosaur dinosaurs whose bodies apparently washed out to sea from the nearby coastlines. Nothing that died in or near the Western Interior Seaway went to waste. The moment a large animal died, whether from predation, disease, injury, or the consequences of swallowing something too large, the scavengers moved in. The Seaway recycled its dead with brutal efficiency. This density of predation did not exist because the Western Interior Seaway was unusually violent or unusually unlucky. It existed because of the specific physical characteristics of the Seaway itself, and understanding those characteristics explains why no modern body of water comes close to matching it. The Western Interior Seaway was warm, shallow, highly productive, and, critically, had no deep ocean refuge. In the modern ocean, prey species can escape into the deep. They can dive into the abyss, into the vast, cold, dark volumes of water below 1,000 meters, where most large predators cannot efficiently hunt because the energy cost of diving exceeds the caloric return. The deep ocean is a sanctuary. It is cold, it is dark, it is nutritionally sparse, but it is safe precisely because predators cannot afford to operate there. The Western Interior Seaway had no such sanctuary. Its maximum depth was measured in hundreds of meters, not thousands. There was no abyssal zone, no midnight zone, no cold, dark refuge below the thermocline. The entire water column from surface to seafloor was within the operational range of the Seaway's predators. A mosasaur did not need to dive a kilometer to find food. It needed to dive 100 meters. A shark did not need to cross an ocean to find prey concentrations. It needed to swim a few dozen miles along the coastline. Warm water compounded the problem. Warm water holds less dissolved oxygen than cold water, which concentrated aerobic life, everything that needs oxygen to survive, into the upper, better oxygenated layers of the water column. This packed predators and prey into the same relatively thin band of habitable water, increasing encounter rates and making it essentially impossible for prey to avoid detection for long. And the extraordinary productivity of the Seaway, driven by nutrient upwelling from the deeper channels and the warm sunlight pouring into shallow water across an area larger than the modern Mediterranean, supported enormous biomass at the base of the food chain. More phytoplankton meant more zooplankton. More zooplankton meant more small fish. More small fish meant more large fish. More large fish meant more predators at every level above. The Seaway was a food production engine operating at full capacity, and the predator guild it supported was the inevitable biological consequence of that productivity concentrated in a shallow, warm, inescapable volume of water. Neither the predators nor the Seaway itself was static. The Western Interior Seaway expanded and contracted over millions of years as global sea levels rose and fell in response to changes in mid-ocean ridge activity, polar ice volume, and regional tectonics. At its maximum transgression, during the late Turonian roughly 90 million years ago, the Seaway was at its widest and deepest. By the Maastrichtian, the final age of the Cretaceous, it was narrowing as the Rocky Mountain orogeny lifted the western margin of the continent and sea levels began a long-term decline. As the Seaway shrank, the predator community shifted in response. Cretoxyrhina, the Ginsu Shark, disappeared from the fossil record around 73 million years ago, roughly 7 million years before the Chicxulub asteroid. Its extinction is not fully understood, but the leading hypothesis involves a combination of cooling water temperatures in the Seaway's northern reaches and the loss of the most productive shallow water habitats as the shorelines retreated. With the Ginsu Shark gone, the Mosasaurs filled the ecological vacuum, becoming even more dominant and more diverse in the final 10 million years of the Cretaceous. New species appeared. Existing species grew larger. By the late Maastrichtian, Mosasaurs were the undisputed rulers of the Western Interior Seaway and of every other ocean on the planet. Mosasaurus hoffmanni, the genus that gives the group its name, reached lengths of over 40 feet in European waters. Tylosaurus continued to dominate the Seaway. Pteranodon, a heavily built mosasaur with robust crushing jaws adapted for hard-shelled prey, diversified into multiple species. The Mosasaur dynasty was at its peak. It would last another 7 million years until a 12-kilometer-wide asteroid struck the Yucatan Peninsula and ended the Mesozoic era in a single afternoon. The impact destroyed the Western Interior Seaway's food web from the bottom up, in the same cascading sequence that killed the terrestrial ecosystems. The darkness killed the phytoplankton. The collapse of photosynthesis starved the zooplankton and the small fish that fed on them. The death of the small fish starved the large fish that fed on them, and the death of the large fish starved the mosasaurs, the plesiosaurs, and every other large marine predator that depended on a functioning food chain for survival. The Seaway itself survived the asteroid by geological standards, persisting in reduced form into the early Paleocene as sea levels gradually fell and the tectonic forces that had kept the center of the continent depressed slowly reversed. But its predators did not survive. Every mosasaur, every plesiosaur, every ammonite, every Xiphactinus, every archelon, every Hesperornis, every giant marine predator and specialized marine reptile that had made this body of water the most predator-dense ecosystem in the history of the planet, vanished in the same extinction event that killed the dinosaurs on land. The Western Interior Seaway lost its monsters first. Then, over the following millions of years, it lost its water. The sea retreated south. The land rose, and the seafloor became the Great Plains. Today, the chalk beds of western Kansas, the Pierre Shale of the Dakotas, and the limestone formations of Texas and Alabama are the primary sources of Western Interior Seaway fossils. The Niobrara chalk, in particular, deposited during the Coniacian and Santonian stages, roughly 87 to 82 million years ago, has produced some of the most spectacular marine vertebrate fossils ever discovered, including articulated mosasaur skeletons with preserved stomach contents, nearly complete Pteranodon specimens with wingspans measured in meters, the shark mummies with fossilized cartilage and skin impressions, and the famous fish within a fish. The Smoky Hill chalk member of the Niobrara Formation, exposed across a wide swath of western Kansas in eroding hillsides, dry creek beds, and road cuts, has been a productive fossil site since the 1870s, when legendary collectors like the Sternberg family and O.C. Marsh's Yale expeditions pulled the first great marine reptile skeletons out of the prairie and showed the world what had once swum beneath the wheat fields. If you drive across Kansas on a summer afternoon, through the wheat fields and the cattle pastures and the long, flat stretches of highway that seem to go on forever under a sky that touches the horizon in every direction. The landscape gives you no hint of what it used to be. There is no drama in the terrain, no cliffs, no coastline, no visible water for hundreds of miles. The ground beneath your tires is dry, sun-baked, and quiet. But that ground was once a warm, shallow seafloor, hundreds of meters beneath the surface of an ocean that connected the Gulf of Mexico to the Arctic. Tylosaurus, 45 feet of muscle and conical teeth, hunted where the soybeans grow now. Cretoxyrhina, the Ginsu Shark, sliced through Mosasaur hide where the county road crosses a dry creek bed. Xiphactinus swallowed prey nearly its own size and died for it in water that is now a wheat field in Gove County. Elasmosaurus swept its impossible neck through schools of fish in water that is now 2,000 feet of empty air and prairie grass, and October combines harvesting grain beneath a landlocked sky. 80 million years ago, this was the most dangerous body of water on Earth. Every depth was occupied by a predator. Every predator was simultaneously someone else's prey, and the fossil record of that ocean, preserved in the chalk and shale and limestone beneath the quietest, flattest, most unassuming landscape in America, is one of the most complete and most violent records of marine predation ever assembled anywhere in the world. The plains remember what the sky has forgotten, and the bones beneath the wheat fields are still telling the story of the sea that used to cover them.